All right, so here is the title for a section that is the best title of all time, Other Types of Equations. I mean that with complete sarcasm. That's Other Types of Equations with me, Mr. Hain, and let's dive right in. All right, so there's a lot of things that we can do when equations look kind of quadratic or just other types of equations, but we're going to be extending the principles that I talked about in the video for 1.5 quadratic equations and applying them to a lot of what we see here. So my first problem, I have 4x to the fourth power is equal to 12x squared. Now I do see right off that these have a common factor. 4x squared, the lowest of the variable powers, is the term. 12 has a factor of 4 in it. 4 times 3 is 12. And I do know that I can, if I take out or factor out an x squared times x squared is x to the fourth. So they have that common factor. So I'm going to make the equation equal 0. I'm going to factor the common factor out, which is 4x squared. So 4x squared times x squared gives me 4x to the fourth, so I know I'm fine. And 4x squared times negative 3 gets me negative 12, so I know that I'm good. And here, if you see, I do have two terms, 4x squared and x squared minus 3, that are equal to 0. So I can apply the zero product rule, and I can solve for x. So here's very simple. I just divide each side by 4, x squared. So I take the square root, and the square root of 0 is just 0. You would recall from before that would have the plus or minus according to the rule for square roots, but 0 has no sign. It's not positive or negative, so 0 is fine as my answer here. And again, I just add 3 to each side here, take the square root of both sides. That gives me plus or minus 3. So I have 3 answers, negative the square root of 3, 0, and the root of 3. So while this problem looked a little bit more complicated, the key was I use factoring when I see the terms share a common factor. So when I factor by grouping, it's used best when there are 4 terms in descending powers of x. So if you look at this problem, yeah, there's an equal sign in the middle, but I've got x cubed plus x squared, and I have an x, and I have no x at all. So I'm going to make the equation equal 0. This is going to be a recurring theme in a lot of what you see me doing for this section. And I now see that I could group the first 2 terms and group the second 2 terms. Now, a lot of people, eagle-eyed people out there, are going to see that I have a negative and a positive here. When I group the negative outside of a binomial term, I'm going to change the sign because I'm factoring out a negative 1. So I factor out a negative 1 from the minus 12, and that becomes positive 12. Again, negative times positive 8x is negative 8x, which is there, and negative times positive 12 is negative 12. So that's probably a little thing that leapt out at you for those that were paying super close attention. I'm going to factor those groups out, and that's the whole reason that I group them, is I see in this first term I can factor out an x squared, is what you see what happened. X squared factored out of the first binomial term leaves me with 2x plus 3. And if I look at 8x plus 12, I can factor 4 out. 4 is a factor of both of these numbers. It's a factor of 8 and a factor of 12. And that leaves me with 2x plus 3. Now, how do I know I'm on the right track? I know I'm on the right track when I factor by grouping because you see the binomial terms are the same. 2x plus 3 and 2x plus 3. So because these are the same binomial term, I can actually factor out that group. That leaves me with just x squared minus 4, which is what you see here. Excellent. I use a zero product rule, and I'm going to solve each one. Again, isolating for x, so I subtract 3 and divide by 2, which gives me negative 3 halves. And here I add 4 to each side, and then I square root, and the square root of 4 is plus or minus 2. So I have 3 answers, negative 2, negative 3 halves, and positive 2. Excellent. Factoring by grouping, again, is used best when there are 4 terms in descending powers of x. All right, so this is going to be interesting. We use these steps, and I hate doing steps, and very rarely will you see me do steps in my videos because I like to think, how can I make something one step simpler or a little bit simpler? That's how I like to attack a math problem or an equation. So we use these steps or this method when a variable is, quote, under a square root, which is what we see here. X plus 3 is under the square root. So the first thing I'm going to do is isolate the variable, radical. So I've subtracted 3 from each side. then I'm going to square both sides. So when I square the square root of x plus 3, that just becomes x plus 3. I don't have to FOIL or anything. And when I square x minus 3, it appears twice because I'm multiplying it times itself. And I FOIL this out, and I have x squared minus 6x plus 9. So the third step is I need to make this equation equal to 0. So I'm going to subtract the x, and I'm going to line it up and subtract with the same term over here. And I'm going to subtract the 3, and I'm going to subtract from the constant term, or c, over here. So I have x squared, because nothing happened to it, and negative 6x minus an x is negative 7x. And 9 minus 3 is positive 6. Now I can factor this. The xbox method lets me factor. In this case, the coefficient is 1 for x squared. So I need two numbers that multiply. 1 times 6 is 6. That's going to be the top number. And then b, which is negative 7. So I need two numbers that would multiply to positive 6 but add up to negative 7. And of course, those numbers are negative 6 and negative 1. Okay. So that's how I get x minus 6 and x minus 1. If I were to FOIL these out, because a is equal to 1, there is no box here. That's the only reason. Again, I want to say that again. Because a is equal to 1, I don't have to do the box. These are just what pop down into my binomial. So x minus 6 times x minus 1 is going to give me x squared minus 7x plus 6. Feel free to pause the video, FOIL that out, and verify that that's true. And again, I'm going to now use the zero product rule to solve this. X minus 6 rather equals 0. Add the 6 to each side. I have x is equal to 6. And then I have x minus 1 is equal to 0. Add the 1 to each side, and x is equal to 1. Okay, so yes, you got to check this. That's step 6. The reason is that whenever we use radical equations, we could... one of our answers could be what's called an extraneous root. It's a root that satisfies the equation or satisfies the method, but does not solve the equation. So we have to check. So that you're going to see me check the 1. So I'm going to plug the number 1 back into the original equation for checkpoint 3. And you see that it becomes 5 is equal to 1. And that is not true. Now this x is a 1 because I am checking the number 1. So since that is false, x equals 1 is not an answer. Now when I substitute the 6 in, this is a 6 and that is a 6, so I have the root of 6 plus 3 is equal to 6. And as I simplify through, I see that 3 plus 3 is 6. This is true. So my only correct answer is x is equal to 6. That does not mean I did anything wrong. It doesn't mean that you did anything wrong. It just means that there was an extraneous root, and that extraneous root was 1. So be sure that you're always checking. All right, you see the words challenge and extension, and I know some of you are going to skip ahead in this video. There's a homework problem that looks like this. Again, I'm not going to hold you accountable. It's for people who want an extra challenge and just want to apply themselves so they can make sure that they understand the ins and outs of this principle. So here you're going to see me isolate one radical, square both sides. So now I FOIL this thing. The root of x minus 3 times the root of x minus 3 is just x minus 3. Plus x minus 3. So that's what I have here. Combine these like terms. I'm going to move and try to isolate the other radical. So now I've isolated the other radical, and I'm going to square both sides. So the square root of x minus 3 is x minus 3, and 1 times 1 is just 1. So that's how I have this little red 1 here. Make the equation equal to 0. I don't need to use the zero factor or use the zero product rule to solve it because I just end up with one solution. So I got to check. So you see, I take this 4 and I plug it back into the original equation. And it is true when I check all of that. So my one solution is x is equal to 4. Okay, I'm going to leave this here for a little bit. Now, when we are solving equations with rational exponents, rational just literally means fraction. So I could have crossed this out and said fraction, but it's the same thing. The book uses M and D, and I get real confused, so I just change the letters to N and D because N stands for numerator and D stands for denominator. So the steps here are we're going to isolate the rational exponent and raise both sides to the reciprocal. And then we have to check our answer because these could also result in extraneous roots. So for our first example, checkpoint 5a, you see here I have 5 times x to the 3 halves minus 25 is equal to 0. All All right, not as hard as you would think. I'm just going to isolate the radical. So I add 25 to each side. And then I'm going to divide by 5, so I only have x to the 3 halves. And I'm going to raise each side to the denominator over the numerator. So this is 3 halves, and this becomes 2/3. So here I have 5 to the 2/3. Now the reason I do that is because when I multiply fractions, I just multiply straight across. 3 times 2 is 6, 2 times 3 is 6. If I multiply a fraction by its reciprocal, it's always going to reduce to 1, which leaves me with just a plain old x, which is what I want. X is equal to 5 to the 2/3. Now I do got to check this, so you see me plug this back into the original equation. And again, this seems really awkward, but then remember that this is just multiplying by its reciprocal, so this just becomes 5. Because the exponents, when you take the power of a power, you multiplying them and they cancel to 1. So yeah, 25 minus 25 is equal to 0, so my answer is absolutely 5 to the 2/3. So we're going to get a little bit more interesting with checkpoint 5b. I need to isolate that radical. So I have x to the 2/3 is equal to 4. And I'm going to see here that I have taken the raise it to the opposite power. And because d is even, I have plus or minus. And so now I have plus or minus 2 to the 3rd power. Now, the way that I got this was that I have 4 to the 3 halves, but 4 is actually 2 squared, 2 times 2. And yes, you're going to have to look for this in the homework assignment, assigned homework questions as well. So when I multiply, 2 times 3 is 6, and 6 divided by 2 is 3, which is how I end up with 2 to the 3rd power. And I'm going to, I have two answers. I have plus or minus 8 or plus or minus 2 to the 3rd power. And when I do check them, I do see that each of these are true. So I know that my answer is plus or minus 2 to the 3rd power or plus or minus 8. Both of those are true. I don't mind which form you guys use as your final answer. Both of them are the same thing. All right. So equations in quadratic form. So we use this and these kind of like substitution method, I guess is what some people have called this, when the equation looks like it's quadratic, but it's a little bit off. In this equation, this is x to the 4th and x squared. Now we would like this if it was 2 and this was a 1. And in fact, it could be. Because x squared squared is x to the 4th, I can substitute h is equal to x squared. So when I do that, if h is x squared, because I know this is true, it's just h squared minus 5h plus 6 is equal to 0. Why go through that trouble? Because now I can easily factor this. I can factor it and I can solve for h. Using the x, and because a is equal to 1, I have h minus 2 times h minus 3 is equal to 0. And boom, I've got what h is equal to. Now remember, in my original problem, you see I'm not solving for h, I'm solving for x. So once I've solved for h, or whatever letter you've used for that variable, all I'm going to do is put the x squared back in. Square root both sides, and I have plus or minus root 2 or plus or minus root 3. That's 4 separate answers, but they all work. Again, they could look like they're quadratic form, but it's a little bit off. So here I have fractional exponents, but the key is the denominator is the same. I have 3 in each one. And look, the numerators are times 1 and times 2. I have 1/3 and 2/3. So because of that, I'm going to use h because my last name is Hain, and that lets me know that I can substitute h and h squared. This lets me factor and solve for h. So instead of saying 3 times x to the 2/3, I have 3 times h squared. Again, because I know h squared is x to the 2/3. 3 times negative 4 gives me negative 12. And b is negative 11, which gives me this number down here. The two numbers that multiply to negative 12 are negative 12 and 1, and they also add up to negative 11. So, positive 1 is how I got this h. The coefficient of h is positive 1. And then the negative 12h here I got from this negative 12. And then the original AH squared and the original C pop into my box so I can factor. Common factor in the first row is 3h, and the common factor in the bottom row is 1. So 3h plus 1 is the first term. The common factor in the first column is just an h, so I factor that out. And the common factor, since both are negative, I know it's got to be negative. And 4 is a factor of both, so here I have minus 4, so h minus 4. Using the zero product principle, I've solved. So h is negative 1/3, and h is equal to 4. So I'm going to go to another slide, but I'm going to put, when I put x to the 1/3 back in for h. So you see what I've done here, and I know I have to raise to the d over n, and d is odd, so I don't have to worry about plus or minus. And here's how I get my answers. Now, I didn't have the work for checking the answers, but I have checked these answers, and you should pause the video and actually substitute back in to our original equation here and see if you again get the correct answer, or that their statements are true. They are true, so I've raised each of these to the third power, and so I have x is equal to negative 1 over 27, and x is equal to 64. Our final topic: absolute value equations. So, is the absolute value isolated? Yes. I just have the absolute value of 2x minus 1. And does it equal a positive number? Yes, it is positive 5. If that was a negative 5, I could stop immediately. And it says no solution. I'm done. No solution because absolute value cannot equal a negative. But since this is a positive number, I can actually solve. Now recall that an absolute value could be positive or negative. The absolute value of negative 5 is 5. The absolute value of 5 is also 5. So when I take the absolute value expression out of the absolute value, I have it equal a positive number or equal a negative number. And now this is all just isolate x, and I have the two answers, negative 2 or 3. And if I put either of those into the absolute value portion of the equation, it would be true. Excellent. So let's look at one that's a little bit more complicated. This absolute value is not isolated. The absolute value here is 1 minus 2x. So I have to isolate that absolute value. I'm going to start by adding 20 to each side, which gives me this 20. And see this 4 that's on the outside of the absolute value. You see that I'm dividing. That's because you cannot distribute into an absolute value. Many students have tried, but you cannot. It will always give you the wrong answer. It might randomly give you the right answer once, but don't get into that habit at all. You cannot distribute into an absolute value. It's like a force field. Nothing goes in. Nothing comes out until you can take that force field down, which is why I'm dividing each side by 4. So now I have an isolated absolute value expression, which is absolute value of 1 minus 2x. It equals a positive number, so I can keep on going. If it equaled a negative number, no solution, I stop immediately. All right. Boom, here I go. I have it equal positive 5 and negative 5. Ironically, I have the same answer, but still you see the steps are the same. I'm isolating for x. And I have x is equal to negative 2 or positive 3. And that's the end of section 1.6. So I guess the key thing to remember is all of the reasons that we use each of these methods. And I would highly suggest you go back and make sure that you have the portions here that are in black or sometimes red, or my handwriting, that says when they're used best, because that's probably the biggest key to solving these equations.